the airways at all. So what you need to do is you put just isotonic salt. So we did this with Gerhard with full lung delivery. But if you just do upper airway delivery, actually you see just isotonic saline. It looks pretty much like the humid room. Even more dramatically if you do a hypertonic saline, because hypertonic saline then is going to be pulling more water out of the epithelial cells into the airways, so you're thickening the fluid, and so you have less surfactant and contaminants, and therefore you have a deeper, more profound effect on, but it still doesn't last very long. So if you thought, oh, this would be an interesting kind of hand washing of the lungs, that wouldn't be too useful because it would take like 20 of these a day. And so we then began to think, and actually this thinking goes back about 15 years, we began to think, well, there are different salts, obviously, in the lungs and in our body. Actually, all the salts that are in the ocean are in our lungs, and the reason is that wherever you are on the planet, you're breathing in salt that comes from the ocean because there's so much sea spray that gets ultimately up in the stratosphere, and so wherever we are, there's more when you're near the sea. Well, there are monovalent salts, the two principal ones being sodium chloride and potassium chloride, and then there's divalent salts, calcium chloride and magnesium chloride. And calcium and magnesium chloride play an important role in the airways, naturally, to clean the surface. Now, why is that? Well, they, on the one hand, then stabilize the surface. With anionic surfactants like DPPC, they have a solvation effect. There's an interaction with the head groups that lowers the chemical potential and pulls the surfactant into the solution and out of the surface, which, as we've explained, actually stabilizes the surface. And then, as I said yesterday, mucus, being a hydrogel, has a thin layer of water that's constantly evaporating and being redeposited from the lower lungs, very thin, that keeps an equilibrium, or tries to, with the air. And below that is mucus, and as with calcium or magnesium, there's a cross-linking that occurs that leads to a rigidification of the surface, and that actually stabilizes the surface as well. And so you might think that instead of delivering 5% sodium chloride, I delivered a 5% calcium chloride, that I might have a prolonged effect. And that, in fact, is true. And so if I deliver out of a system like this about 20 milligrams of water with about 5% CaCl2, the exhaled droplet stays low for about 5 hours. We've done a lot of these experiments over the last couple years, and the duration is about typically 4 to 6 hours, and this is magnesium chloride, so it's not an ion-specific effect. And so we've now done 7 randomized studies with a nasal saline control in different cities and countries, in very dirty environments and very clean environments. We talked about the Bangalore studies with Kara, but we also did studies that we haven't published in LA a year ago in the fall when they had the big smoke problem, and we saw very much what we saw in Bangalore, where we had people who were breathing out 50,000 particles per liter. So breathing dry air or breathing dirty air definitely fragilizes the surface, either by thinning out the airway lining fluid, or just putting more particles directly onto the surface, and makes the surface want to break up. Now, does it matter, right? And so it seems intuitive that as you create droplets on inhalation in your upper airways, and as I mentioned, we do see a lot of lower airway formation, particularly, even especially when you breathe really deep. But it seems intuitive that that would increase the probability of contaminants getting deeper in the lungs. And so in the spring, and I will just say a few words about Carol's study. So in the spring, so we have been, we got to people about a year ago a form of what we call FEND, and about 10,000 people have been using it in the United States, and we've learned a lot. People use it 3 times a day, morning, afternoon, and night, to keep their airways hydrated. The question is, well, what benefit does that bring? And by the way, we brought this into human testing as a nasal saline. Nasal salines in the United States are regulated as cosmetics. You need to market them as cleansers, which they are, cleaning the respiratory droplets. And so people have been using this cleansing, this airway hygiene, 3 times a day. And so Carol had been doing a study, as she mentioned, in COVID-19 patients looking at exhale aerosol. And as other people have mentioned, Chad Gerhard, infected, you get a lot more particles. She sees that. And then when the second wave, the Delta pandemic hit, from my perspective, my dialogue with Carol, I was just really fascinated and horrified by what she went through. And I'm really glad you spoke up a moment ago about the reality that you're facing at the time. And I've said to many of you, she was hospitalized in the midst of this after having been vaccinated, was on oxygen. She lost several members of her team, died. Incredible that in the midst of that, she decided to do a random control study, really rigorous study, wherein, if it wasn't clear, 40 people came in, recently detected. If they weren't on oxygen, and they volunteered, they were put randomly into a nasal saline control group where they took 3 times a day for 3 days, simply saline, spray, or they took fen 3 times a day. And as she mentioned, we saw symptoms go away in the fen group. Drug rescue therapy, steroid and antibiotic injection went down radically in the fen group, but even more intriguingly, oxygen saturation went up. And so that led us to think, why would oxygen saturation? Normally, oxygen saturation would be reflecting lack of permeation of oxygen in your gas exchange regions of the lungs, of what's going on. And so we all got Apple Watches and have been doing lots of studies, and now a formal study in exercise-induced dehydration. And what we find is that in addition to the respiratory droplet change on dehydration, there's a glottal aperture change, and there's an oxygen saturation diminution, which clearly happens in COVID-19 in the early stages of COVID-19, but it also happens in exercise, by the way. And if you hydrate the upper airways, as has been done now for many years for phonation reasons, for much the same reason, when you hydrate your larynx, your threshold pressure goes down, so it's easier, it expands faster and better, and that leads to an oxygen benefit. So it's a super interesting consequence. And so what I want to finish with is just to say, as was alluded to by many here, Dick did, Fan did, among others, there is a really deep literature at this point on the benefits of breathing relatively humid air and the dangers of breathing dry air for a range of central and lower respiratory tract diseases, which is, again, interesting because it's upper airways and it's having this impact on the lower airways. And so for all of those reasons, we believe that it's really critical, particularly in those regions of the world where water itself is very hard to come by, and where the air is the dirtiest, as we heard earlier, it will remain dirty and get more dirty probably for a very long time, that particularly kids who are on the planet and will be breathing planetary air longer than anybody should have clean airways. So this image actually comes from the UNICEF website, where there's an encouragement to get kids to wash their hands for the COVID-19 pandemic. And so we would argue that it's actually even more critical that they wash their airways. So thank you.
Okay, thank you, Professor Edwards. And now we have our next speaker, who is at Berkeley University in California, and who has gotten up very early to join us via Zoom. Professor Yagi has thought of things that you never knew existed, and this is in part because they did not exist until he thought of them. Professor Yagi is a pioneer of reticular chemistry, a new field of chemistry concerned with stitching molecular building blocks together by strong bonds to make open frameworks. Perhaps his most recognizable work is in the design and production of new classes of compounds known as metal organic frameworks, or MOFs. Reticular frameworks are noted for their extremely high surface area and very low crystalline densities. Professor Yagi is also the pioneer of molecular weaving and synthesized the world's first material woven at the atomic and molecular levels. He's been leading the effort in applying these materials in clean energy technologies, including hydrogen and methane storage, carbon dioxide capture and storage, as well as harvesting water from the desert. We will now hear from Professor Yagi, who will discuss what he calls the air economy, powered by reticular chemistry for clean water from air, clean energy from air, and clean air. Thank you, and welcome.
Thank you very much, Laurie. And I've been watching the proceeding of the symposium on YouTube, and I'm both impressed and of course, I learned quite a bit from this unusual symposium, very nicely put together. Thank you, Laurie, for doing all the work. And I want to thank the organizing committee, including the inspiration by Bengt Norden, for these extremely informative conferences. I would like to share with you my thoughts on how we can address some of the most vexing problems facing our planet. And so it's a slight shift from the lectures that have been given already, but I want to share with you this new chemistry that we've developed over the last 30 years, we call reticular chemistry, and how this is powering what I envision would be the air economy, meaning to use components of air either to clean air or generate energy and clean water. So the molecules that are responsible for these problems that are facing our planet are some of the smallest molecules known to us. Hydrogen, the vision there is that hydrogen can give us energy without any byproducts except water. So it's a clean fuel. And cleaning the air from carbon dioxide, I should say that the levels of carbon dioxide in the atmosphere right now are slightly above 400 ppm. That's almost double what it used to be before the Industrial Revolution. So I want to show you how we can trap carbon dioxide from air and then how we can extract water from air to produce clean water. So let me just step back and just say that the development of civilization, progress of humanity has always tracked with the discovery of new materials. In fact, we have ages that are named after materials that have been used and fashioned to serve humanity. Stone Age, Bronze Age, Iron Age, Glass Age. We actually give them names: Steel Age, Aluminum Age, and Plastic Age. All of these, the more sophisticated we have gotten at manipulating them on a finer and finer level, the more we can make use of them and the more that they have served us. And so we are very familiar with the molecular age because it is the age that gave us pharmaceuticals and has made a big impact on the world. Today, I want to make the case ostentatiously that we are viewing the age of reticular age, where we control matter on the molecular level, but we not only can make zero-dimensional or large cages of compounds, but also materials that extend infinitely in 1 dimension, 2 dimension, and 3 dimension. I think you'll see that this is not just an empty claim, but indeed that this is real, and that the expansion of this chemistry is leading us to believe that we live in the reticular age, which is going to address these problems that I'm talking about and many more. And the reason it's so powerful is that it makes use of the periodic table. which is the hope, I would say, for humanity. We are able to combine elements in the periodic table to make molecules. That's what chemists do. And with reticular chemistry, we are able to take those molecules and stitch them together to make incredible materials that can be fashioned on a finer and finer level so that they are suited for a particular application. So what is reticular chemistry? As Laurie already mentioned, it is linking of molecular building blocks by strong bonds to make crystalline extended structures. And there are three components in this definition that are key to this new development. One is that we're using building blocks, well-defined building blocks, and we're stitching them together through strong bonds to make durable materials. That's why I emphasize strong bonds, is that if you have a material that's extracting CO2 from air, you want it to be in the power plant year after year after year before it quits on you. And so that you don't have to replenish it every time you have a CO2 capture and release cycle. And the same thing with crystallinity is very important. In fact, this is the development over the last 30 years that has changed the way we think about extended structures, is that we're able to not only link the molecules together by strong bonds, but obtain them in crystalline form instead of a disordered form, which was the usual way before our work. So crystallinity gives you homogeneity of the material so that it behaves the same way over and over again. And these materials look like this. These are crystal structures of the first class of materials, metal organic frameworks. And you can think of them as made from hubs and spokes, or from, let's say, struts that are linked by metal oxide units. These metal oxide units are joined by simple organic units to make extended structures. And we use the yellow ball in this case to indicate the space that has been thus created into which one can trap those gases that I was talking about before. The flexibility of this chemistry allows us to also go beyond just metal or containing frameworks into entirely organic frameworks, covalent organic frameworks, which have extended organic chemistry to the infinite 2D and 3D dimension. And as Laurie already mentioned, we have developed molecular weaving, just another testament to the level of control that we can have on the molecular level. So I won't talk about molecular weaving today, but I'll give you some examples of how MOFs are beginning to solve those problems that I'm talking about. If your eye could be looking at the atomic level, you would see a MOF structure that looks like this. And you can see that they have pores, but they don't have walls. They're like scaffolds. And everything you're looking at, from the metal oxide unit to the faces of the six-membered rings and the edges of the six-membered rings, all of these can serve as adsorptive sites onto which one can bind hydrogen, methane, carbon dioxide, water, because we are able to modify the interior chemically to be suited for a specific application. And this is what's new here. It's not just that they are highly porous, and as you can see, with extremely high surface area, 6,400 meters square per gram, but also that you can go in and chemically modify them so that the pores can be suited for a specific application. You can't do that with any other material. And this is, I'd like to point out that in 1 gram of MOF, you have the surface area of an entire football field. Today, there are MOFs that are being made that are approaching 10,000 meters square per gram. That's over a football field. And that's the space onto which one can bind those gases. So the area has mushroomed over the last, since our first report back in 95. And now in 2020, you can see that over 100 countries have groups, research groups that are investigating and studying MOFs and COFs, or this chemistry in general. So I want to give you 3 examples, one on hydrogen, one on carbon dioxide, and one on water, as to the results of what we are trying to do here with these materials. This is hydrogen, as you can see here in white specks that are floating in the channel. But you see that they're not just floating in the channel, but they are adhering to the adsorptive sites that are part of the framework. The framework is in red. So that's the MOF framework. And you can see that if I didn't have the MOF framework, the volume that these hydrogen molecules would occupy would be double the size, maybe even more. So the MOF itself allows you to compact the hydrogen molecules into smaller volume under mild pressures and reasonable temperatures, so that it could potentially become economical to use as a fuel. So where are we today? Well, since 2002, we've made tremendous progress in the amount of hydrogen, this is grams of hydrogen per liter, by modifying the interiors of the MOF. Here's the metal that is part of the MOF and the linker that is used. And these are, you can see that we can vary the components, and as such, depending on the polarization effects that we introduce, we can bind more and more hydrogen. We can store more and more hydrogen. Just for comparison, this is hydrogen gas at 350 bar without the MOF. And this is hydrogen gas at 700 bar. This is at 1 bar. This is liquid at 20 Kelvin. So we're interested in these uptake levels. Now, with MOFs, we have achieved 58 grams of hydrogen per liter. More recently, there are reports of even higher uptake, but that's at 77 Kelvin. Now, 77 Kelvin is extremely hot compared to liquid hydrogen at 20 Kelvin. So we're doing okay, but we're not yet ready for automobile fueling. We need to bind the hydrogen a little bit stronger, specifically at 20 kilojoules per mole energy, binding energy, to be able to store enough hydrogen so that it's useful for automobile fueling. However, at 77 Kelvin and 12 weight% hydrogen storage, a lot of these trucks that you see on the highway are transporting hydrogen under nitrogen temperatures, so at 77 Kelvin. So when these trucks, you could take this material right here, and if you put that in the truck, you can store double the amount of hydrogen. Even though the MOF occupies space in that volume, still you can store double the amount because of the effect, the compaction effect that I showed in the movie of hydrogen by virtue of its binding to those adsorptive sites. It's almost like taking bees and introducing a honeycomb, and then the bees are compacted on the honeycomb, so that you can, in fact, store a lot of hydrogen. This is quite a bit of hydrogen, 12 weight% of the material is just hydrogen. You can store a lot of hydrogen in very small volume at reasonable conditions. So hydrogen, we're not ready yet for automobile fueling, but certainly we have achieved the level where it's interesting for storage, for stationary storage, as well as transporting hydrogen in those transport trucks that I've showed you. There are 20 gigatons of hydrogen that are being produced today. Annually, they are being transported, as you see in those, in trucks like that. So we think that there is potential there for use of MOFs. Now, with the carbon dioxide capture problem from air and from flue gas. So the thing that you should know is that CO2 in air is a very small amount, although double what it used to be, as I said, before the Industrial Revolution. We have to bind for the carbon dioxide from about 400 ppm in the atmosphere. And from point sources, from point sources, it's a little bit higher. It's a little bit easier to bind it from flue gas. much harder from the atmosphere because you have to process a lot of air. You have to push a lot of air through the material to capture the CO2. And one of the main things that you have to be able to do is to separate CO2 from a whole list of gases such as oxygen, nitrogen, including water. And water, for the most part, could play a constructive role, but so far it's been playing not a cooperative role in the binding of CO2. However, I will show you some recent evidence that we have materials that operate in the presence of water, and in fact, the binding of CO2 is helped by water. So what are the requirements for having a carbon capture material? You need a material that has high capacity. So a lot of those adsorptive sites that I've talked about. You need water stability because there's plenty of water in the atmosphere and plenty of water in flue gas. So you're going to be binding CO2 and water is going to be competing for those adsorptive sites. And the material has to be stable in water. You're binding CO2 in the presence of oxygen. And so oxidation of the elements that are introduced in the material to bind CO2 is going to happen. So you need oxidation stability of the material. We need cyclability. We need to be able to cycle this over hundreds of thousands of cycles for many years. And we need regeneration to be able to have a low regeneration temperature, meaning instead of heating to 300 degrees Celsius to remove the captured CO2, we need to be able to remove it under mild conditions. So there are good news and bad news. The bad news is that there are no materials that meet these criteria today. You can see here every red X means that that material failed in these minimal requirements: the capacity, the regeneration temperature, and the cyclability. Okay, so the aqueous amines, yes, they are used to capture carbon dioxide from natural gas that is being mined, where there's about 15 to 20% CO2, but they are dirty, they are environmentally unsafe, they are corrosive, and they're just not viable for a long-term use in power plants or to capture CO2 from the atmosphere. And the regeneration temperature, just to give you an example, if we're going to use aqueous amines in power plants, almost 1/3 to 40% of the power generated in that power plant would have to go just for the CO2 capture process, because carbon dioxide is being bound covalently, and you're also heating water, which has high heat capacity. Cyclability is not good. They break down after a few cycles. Carbon doesn't work. Zeolites don't work. Resins, there are some organic resins that seem to be working okay, but they have this regeneration temperature problem and so on and so forth. The good news is that MOFs are emerging as potentially satisfying a lot of these criteria. And so there's a lot of research. Unfortunately, DOE is funding a lot of MOF research right now to capitalize on this potential and interesting preliminary results. This is just one experiment that I just want to share with you, that if I have air here, 0.4 millibar of CO2 in the air, and I have my material here, this is a MOF, 1 kilogram of MOF, and you pump the air into the MOF, you see what you get on the other end is going from 0.4 millibar to less than 0.02 millibar. And that tells you that we are able to, this is a real experiment using real conditions here. And it shows that we have materials that can bind CO2 from air. And the regeneration temperature is not hundreds of degrees Celsius, but depending on how fast you want to do it, it could go from 40 degrees to 90 degrees. Now, from flue gas, from a power plant, say where you have 15% CO2, you can reduce that down to 2%. So there are, I would say, we are working on materials such as this one. This is a This is a moth that has been decorated and functionalized in the pores with glycine. Glycine with its NH2 group is highly selective to CO2 in the presence of water. This is a highly porous material, and this is what we are using here in this prototype. So we're very excited about these results. They show that, in fact, you could capture carbon dioxide, could clean the air from carbon dioxide, and you could trap CO2 from flue gas. I want to show you how, in my last example, how we can introduce water and air as a resource for drinking water. And I need not tell you that water is one of the major problems in the world. 1/3 of the world lives in water-stressed regions. And even in the watered regions of the world, questions of water purity still persist. And also many countries import their water. 160 countries import their water. So for many countries, this is a national security problem. And the problem is projected to get worse. This is in 2040. Even countries like the US or Midwest or East Coast of the US is projected to be water stressed because we're using a lot more water from the underground water than it's being replenished. And so that's this situation is getting worse. So what have we been doing about that? So the idea is that perhaps we could harvest the water from air. There's almost 13,000 cubic kilometers of water in the air at any one time. Okay, that means almost as much water as we have in lakes and rivers on our planet. So there's plenty of water. And before any of you ask me about drying the air and leaving us without water to breathe, if we're going to serve 50 liters of water a day per person that's living on our planet, we would have only used a very tiny fraction, less than 1% of this water. There's plenty of water in the air. And just recently, we published a science paper that showed how moths could be used for water harvesting. And in this science paper, we showed how water goes into the pore, and we've identified the sorptive sites within the moth. This is one pore of the moth, as you can see, and we can expose the interior, and you can see water molecules in red sitting in specifically designed places to capture it from air with low humidity. So from those regions, those red regions I showed on the previous slide, to fill the pores. And because you have very high surface area, you have many sorptive sites, and therefore this material takes up almost 40% of its weight in water. This is so promising that we have been testing these in the desert. So this is a device that works on nothing else except ambient sunlight. It's made of two boxes. One box has the moth, into which air goes in, water is trapped in the moth, and then during the day you close this outside box and expose it to ambient sunlight. The inside heats up, water comes out of the moth and condenses on the walls of the larger box. So from 1 kilogram of moth, we can harvest 1 liter of water per day with no energy input aside from sunlight. That's pretty powerful because the moth stays in the device, as I said, for many years. It's been tested over 250,000 cycles, and it's very stable. So it does not need to be replenished. This is a device that can sit in a corner somewhere and harvest water. Okay, so if you want 2 liters, then you can have 2 kilograms of moth. However, you could harvest a lot more if you can do more than 1 cycle a day. And for that, if you use an electrified device, this is our latest prototype, you can harvest 4 to 5 liters of water per day. Okay, and that's from using 200 grams of moth. 200 grams of moth, being able to do more than 1 cycle a day, you can harvest up to 5 liters of water per day. Okay, that's enough for the drinking needs of a small, let's say, 4-membered family. So we're taking this further, and we're making now larger and larger devices that can deliver even up to 20,000 liters for a small village. So we think that this technology is viable. Clearly, we can do it with electrification or without. And I think here the development, not only that we're using water in the atmosphere as a resource of water for drinking and for household use and agriculture, because it's, by the way, I should mention that it is pure water. We have tested it and it meets the FDA and standards for drinking water, absolutely no metals, no organics. The MOF itself, as I should have mentioned, that the MOF itself is a filter because its pore size is just small enough to fit the water and prevent anything else from going into the pores. But what we're doing here is we're making water distributed. You can personalize your water. This is a device, the electrified device is supposed to be a kitchen sort of appliance, can personalize your water. The water is pure, and hopefully my vision is that the world would achieve water independence if we can take this further and commercialize it in widely. So the technology works. There's plenty of air, plenty of water in the air. It's a cheap or inexpensive resource. It's a free resource, and the water that you get out of here is extremely inexpensive. So this is just my idea about using these materials to harness the power that we have in chemistry to trap either contaminants from air or useful molecules like water from air to solve some of the problems that are facing our planet. So thank you for your attention and for the opportunity to talk.
Thank you. Thank you so much, Omar. About a year and a half, Professor Norden and I put together a conference in Stockholm, and Omar was there and actually showed us how he harvests water from the air on stage. So it was very impressive, and we know you can do it. So thank you. So we now look forward to hearing from Professor Bent Norden, whose scientific expertise represents an exceptionally wide breadth and scope. He is a physical chemist with an interest in structure and interactions in biomolecular solution systems. His pioneering contributions cover a range of physics and chemistry. Professor Norden has designed several now famous constructs. He is also the former chair of the Nobel Prize Committee for Chemistry. He's the founder of Molecular Frontiers Foundation, hosted by the Royal Swedish Academy of Sciences, and the editor-in-chief for Molecular Frontiers Journal. Professor Norden expresses optimism about our possibilities to mitigate challenges that currently trouble planet Earth. As he indicates, we know how to utilize solar energy to produce electricity and how to produce hydrogen gas by electrolysis of water, as well as how to combine hydrogen and carbon fuel cells that combine hydrogen with oxygen from the air and produce only water as exhaust. These can and will be used to run cars. Once convenient ways for storing and distributing hydrogen are developed. With this in mind, Professor Norden will quite simply offer us a scientific recipe for saving the world. Hopefully in 15 minutes, right?
Thank you, Laurie, for letting me give the concluding talk of this exciting conference. I think all of you have been struck by the multifaceted nature of the problem area that this meeting is addressing. And I took down 3 bullet points that I think covers what we have heard during these days. And the number 1 is knowledge is growing, fortunately. This meeting, not least, have shown a number of examples of paradigm shifts that's surprising new views and solutions and their impact. 2, injustice of climate change. I think Dan Schrag did an excellent overview of the climate change and its impacts, including unfair effects on living and health, depending on where you live on the earth. 3, political challenges. I think the political dimension may be really the hard problem here. From the local economy, financial legislation, to the global collaborations that we need to establish to address the problems. So who am I to give you the doctor's prescription of what to do? And I changed the title by adding a question mark here. I'm just a physical chemist, and what you will hear now is just some common sense reflections. It's based on an idea that Sir John Thomas, who passed away last year, of the Royal Society, and Professor Paul Alivisatos, now president of Chicago University, came up with some years ago and called the AN view, and we developed it in a project that we addressed to Angela Merkel. And she will get a copy of this talk now again. Because the idea, Alivisatos being born in Greece, was that the difficult situation in Greece, the hard debts, should be possible to be paid back by letting them install an industrial evolution and deliver back energy to the north. So I have a number of questions, and the first one is, how serious is the climate change? And it depends on who you ask, but it is a serious issue, and we have to do something. The question is, are we doing the right things? And this is a matter of priority. Are we able to prioritize? Are the politicians able to give the right priority? Is there a risk that we, if we don't do enough, come to a tipping point where the process is irreversible? Besides getting rid of fuels that produce emission of carbon dioxide, what immediate hands-on actions could be deployed to mitigate the climate problem, and which are realistic? Do we underestimate? How do I get back this? Do we underestimate challenges? Let's see, doesn't work. So that we can't give do the right priority order. We could also ask whether those who are very active in the field, and we notice that there are commercial interests, people are happy to hijack a problem. And so we could ask whether some independent peer reviewers might come up with a different priority order. We may even question whether our totally established concepts, sustainability and renewable energies, written into all kinds of manifests today in politics, all universities have it in. Is there a risk that they make us blind to the realistic solutions? Decision makers are often said to be reluctant to react strongly enough in addressing climate change problems. And We all agree about that. But do scientists have a role here and opportunity to convincingly align in both people and decision makers? As we heard before by Dan, Svante Arrhenius was a pioneer here. He predicted that doubling the carbon dioxide concentration should lead to a temperature increase of 6 degrees. Some years later, he modified it to 4 degrees, which is quite close to what Sherwood and company in just last year calculated. And I could say that Arrhenius' theory was verified and improved. The main improvement was that the heat transfer by convection was included. And the one who is responsible for this is the Japanese meteorologist Syokuro Manabe, who received this year's Nobel Prize. So my prescription here is that we should use what we have, and we should do it in a very simple way. We have already excellent materials for making solar energy, solar electricity. There's a lot of research and improvements going on, but we could use what we have, the simple crystal silicon, which is what you see everywhere. In the future, we will probably get perovskites in crystal states, and you place it on suitable sunny places, Sahara, Greece, Sicily, Spain, where electricity could be delivered via power lines, or it could be used to use another very simple process, namely to produce hydrogen gas locally by electrolysis of water. This is an experiment that I remember I did at school, in the high school, and it's extremely simple. You make an alkaline solution that's a high pH. That makes it possible to use the hydroxide ion as a transporter of charge, but it's renewed, so you don't have to add anything, and the total process is just that you decompose the water into hydrogen and oxygen, and you could collect the hydrogen at the anode. No, at the cathode. You let the oxygen go out in the air. So imagine an experiment where we hire a small land here, let's say 6 kilometers in not too far away from water, and the solar energy we can gather during the solar sunny hours is enough to cover the electric energy problem in Sweden. If we in the future should cover all energy needed, that is including the fossil fuel that is used today, we'll need a bit more. We need 10 kilometers by 10 kilometers. On this map, I've also put in, a little provocatively, a water cube, which corresponds to the meltwater if all ice on Antarctica melts away. And recent findings indicates that anthropogenic actions indeed have caused an accelerated melt. And this is, of course, a very serious phase of the climate change. So this cube, which is, of course, unreasonable to create, it should be 300 kilometers high, or if we let it be a lake, which is 1 kilometer deep, it should be 5,000 kilometers times 5,000 kilometers. So it would be a big bit here. But it illustrates the possibility of mitigating the effect by taking care of this water. This is 95% of all clean fresh water we have on Earth. And that's another important aspect of the climate change. We need to deliver fresh water to people. So imagine that we disperse this cube into small cubes dispersed all over the earth. So here I've put down solutions. They are ordered by me in what I see as falling feasibility, but I think they are all important. Hydroelectric power, if we take mountain-rich countries like Sweden and Switzerland, it provides a big fraction of our electric energy. But we have no model for how to store the energy. And this is one of the serious problems. We need some means, and one possible mean is hydroelectric energy storage. That means that you pump back the water to your magazines. Thank you. It was, I call it the Switzerland model, because it was the first time developed here, 1907. And nuclear power we will need. We will need it for some 40 years until we have deployed solar power and hydrogen power. Hydrogen power, that is hydrogen gas, which we heard from Omayagi, is also a possibility to provide an energy storage. Then I see the photosynthesis in plants, a very important solution to our problem. The plants will absorb carbon dioxide and generate oxygen. We could plant new trees, but the production of oxygen and absorption of carbon dioxide is asymptotically declining, and so you have to cut down the trees and you use the tree for a building. Maybe you replace concrete and cement with the tree, wood. And that might mitigate another problem, which I come to in a moment. Of course, wind power is very important, but the problem is that it's intermittent. In Sweden, when it's really cold and we need electric heating in the houses, it's completely calm. There's no wind power. So the intermittency property makes it necessary for us to have some way of energy storage. And again, it would be good if we have some way of mitigating the land ice melting. We see that land ice on mountains and is a serious threat. And if we just take Antarctica and melt it away, it corresponds to almost 60 meters, 58 meters sea level rise, which is a terrible effects to many parts of our globe. But it might be combined with the new geographically spread clean freshwater reservoirs, and they might also be used for hydroelectric energy storage. So this may be a direction worth considering. I put on a list of less competitive, but I'm a little provocative here, and we just heard from Omayagi that carbon capture is feasible, and I said we should abandon it, but I think I changed my mind. The carbon dioxide, if we collect it, if we capture it at the source, at the factory where it's produced, then it could be used, and it could, for instance, be combined with hydrogen to produce methanol, which could be a useful fossil. And I also am skeptical to fossil gas and biogas. maybe this could be discussed. We have a number of other forms of energy, and the geocapture I thought was, until my breakfast with Dan this morning, was that it could be potentially hazardous. I changed my mind there too. I think that it could be stored in a reasonably good way. I don't know if you know that hydrogen gas is produced. It's used in industrial context, and the yearly production on this earth is 7 times 10 to the 7 tons. But it's produced in a very dirty way from fossil gas. We could store the hydrogen in various ways, but what I want you to recall is that this is the cleanest conceivable combustion. Maybe not in a furnace, because then you have nitrogen as well, and you get nitrogen oxides. But if you do it in a fuel cell, the only exhaust is water, so it's extremely clean. And we should aim for this, just as you heard from Omar Yagi. We could potentially store it in MOF cages, as you heard. It could be transported in various ways, or it could be converted to liquid fuel. And this was what I said, that if you capture the carbon dioxide and combine it with hydrogen, you could produce methanol. This could be done at high pressure and high temperature, and then thermodynamically it's a very favorable reaction. You could do this. However, it's still a carbon fuel, just like biofuels, and it will produce carbon dioxide. The energy storage, I think I mentioned the pumped hydroelectric energy storage. The first time was here in Engeweir in 1907. And the idea is that during periods of high electrical demand, stored water is released through the turbines to produce electric power. Reservoirs usually small compared to conventional hydroelectric plants. And this is an economical issue. With solar energy, if you could use this as a battery for the delivery of electricity during night, it's okay. But if it's wind power, which is, it could be calm for several weeks, it is really an issue. Hydrogen is another possibility to use as a battery, and of course a normal lead battery. But so the energy storage is a problem that has to be addressed. So let me return to my questions here. Are we soon approaching a tipping point? And there is no scientific evidence in support that the process should be irreversible. That is not comforting, but we should not panic. We should do something clever. So besides decarbonizing fuels, which is our primary goal here, what immediate hands-on actions could be deployed? And do we underestimate challenges and therefore cannot correctly assess priority? So the first point is, of course, we should stop using carbon fuels, including renewable ones. We should develop hydrogen gas fuel produced by electrolysis of water. That's the cleanest form of hydrogen. We should develop solar electricity, but we should do it at sunny latitudes. It should be realistic that we could deliver enough electricity. And until we have deployed 1, 2, and 3, we need to go on with nuclear power. And we need to subsidy it. In Sweden, we tax it and make nuclear electricity extremely expensive. And we need to develop energy storage systems, for instance, by stored hydrogen energy. And we should try hard to mitigate land ice melting and maybe also build other clean freshwater reservoirs available to all people. So, as to the political expert panels, there is no consensus, as I can see it, about priority here. People are suggesting many things at the same time. I think this is a problem. Do concepts like sustainability and renewable energies make us blind to realistic solutions? I think one should be probably cautious here, because this is like what Martin Luther reacted against. You know, how you could make yourself feel good by paying something. I think I was too hard here about carbon capture. There are exceptions. Decision makers, often said to be reluctant and so on. Well, I think scientists should interact, but they have to be, it's extreme complex, so they have to be careful. And we should avoid the situation where we go out and promise something. We very easily end up in the cry wolf position if something turns out to be wrong. That will be turned against us. So the conclusions, there are already feasible solutions, but we should focus on the simplest, with priority to sunlight energy converted into electric power and hydrogen by electrolysis of water. I may be wrong, but this is what I say we should do. We should decrease all CO2 emissions. We should find some way of storing electric energy. I focus very much on electric energy here. We could store hydrogen, or we could put back water into hydroelectric reservoirs. But the most important one, I think, is to solve economic and political challenges to establish required international energy collaborations. I mean, how do we accomplish the collaboration between Greece and Germany? It's possible, but between states in northern Africa and Europe, it's extremely tough. We have to be prepared to pay. But I think that could be good. We tried to make Angela Merkel interested in this, and some of her advisors didn't think it was a good idea. Well, thank you.
Sit over there. Okay. David? So I want to thank all of you again today for this spectacular day, yesterday as well. We're going to have a couple questions now for our speakers, and then we can continue the discussion across the hall where everybody is invited to lunch. Those of you who have time, at 3:30 we're going to have a bus give us a little tour of the area, including a World Heritage Site, so you're welcome to join. But first, let's take a couple questions for our speakers, and thanks everyone again so much. Omar is with us as well. Okay, yeah, go ahead.
Really fantastic talks, and I guess this is to everybody, but principally to our last speaker. I support the kind of political, personal political activity of recycling, and probably most importantly, personal and family energy use. But I do wonder to what extent campaigning in this area distracts from the really important issues of lobbying governments and powerful organizations to change their energy policy. And I'd just be interested in your thoughts about wouldn't we be better spending our efforts lobbying instead of obsessively recycling?
That was to you, I believe.
I think you need to do both. Because if you are going to install a technology, a very detailed technology, you have to have the plan. And that has to be discussed with the few governments that are to be involved. Of course, at the same time, you have to do the general lobbying to go the right way. Yeah.
I think we should hear from Omar maybe on this as well, since you are introducing new technology.
Yeah, I would say that, you know, a lot of problems, I think, well, let me just say that what I said about the periodic table, I mean, in that all these problems can be solved if our will is there and the resources are put to solve them. Because the periodic table is really, it really is the hope of humankind. We know how to use it, and we know how to make useful things that that can solve these problems. I think for the first time in a long time, you know, let's say the carbon problem in the atmosphere has to be solved. Even if we stop producing CO2 tomorrow, we still have to take the CO2 out of the air because it's doing damage. But here we are, like the pandemic, we have not faced this problem head on. We don't see any united front from all these countries in the world that to say this is a problem that we need to solve. Okay, so we need a united effort, just like, let's say, going to the moon. Okay, that inspired generations. We need to also have a united effort to solve this problem. I am not hopeful on that front because it doesn't have to do necessarily with science as much as it is with social aspects, considering how badly we have managed the pandemic on a global scale. So, but I think the solutions are there, and with enough attention from funding and appropriate funding, not task-oriented funding, but funding that allows the scientists to go in and solve the problem without somebody breathing down our neck. I think the solutions are there. I showed you our effort in capturing carbon dioxide from air. Okay, that's now is a collaboration with GE to take it to the next step, to the system level, and make it energetically economical to do. So these are problems that are being solved, but like Bengt said, we need a joint effort to address them.
Thank you. In the back there, please.
Yeah, my question is about partly some of the previous presentations and this one. We spoke about, or it was spoken about, that there was a tremendous injustice in terms of climate, and there's also, when we look at what you've spoken about now, an injustice in the use of resources and therefore the generation of economic activity for people. Surely there is, by rectifying those injustices, not in terms of people paying a little bit more and helping people buy solar cells in third world countries, but in actually looking at the efficiencies of the current neo-colonial system of resource use and manufacturing. And the question is, there's been no concentration in solving the problems in actually restructuring our economic systems whereby we're not moving resources halfway across the planet and back. Now, you mentioned the use of timber. It happens to be the business that I'm in. 80% of the cost of the production of timber is transport. The balance of that is in getting hold of and developing infrastructure, which is at a massive scale, because you've got to have big transport. Now, surely if we're addressing those problems, we start radically changing the consumption of energy and therefore reducing the problem that we have with carbon dioxide, because we're just not generating that much.
Any comments?
Well, maybe I'll just make a general comment. I'm the least relevant here, but I think I'd like to also echo Omar, and maybe I have a question for Omar too, but in response to you, Alan, I think that we're a small group, so a little bit of a change of tone here. I think a major issue that we're dealing with, and Bent, you summarized it really well. There are, people are and have always been good at figuring out solutions to their problems, and we've become really good at learning how to translate those. We're much worse at, and we're actually really good at collaborating, as we all have been talking about, on small scales. We're really bad at collaborating on a global scale, and it's probably not until we've got a 60-meter rise, and anyway, so that's a problem, and there's a really short period of time right now, and I think that one path forward, and I would even throw this back to you, Alan, and I think is what you do, is to actually do something. And I think generally when we do something that we actually have a capacity to do. And so I think what Omar, you're doing is amazing. I do have a question, and so I think for this group, having a focus on, well, what can we do? And so there's obviously big meetings happening around the world at a more global level, and Dan made a really good point about the fact that we can be nationally racing forward, but this is a global problem, so it's really an immense issue, but we can do something, and I think possibly really catalyze change at a local level that becomes global. So, Omar, my question to you is whether in the scaling up, all three of your solutions seem really both clever and potentially practical. Lots of issues at the scale, as you scale, and questions, but one of them has to do with just where do those materials go at the end of their life span, particularly as we have many more of those. So how much have you thought about that?
Yeah. So we have thought a lot about that, and we've collaborated with BASF for 17 years and demonstrated that these can be scaled up, these materials can be scaled up to multi-ton quantities. And the nice thing is, although in my lab we discover them in organic solvents, but when you are at the scale-up level, you can always go to water. You can make the same compounds in water. And I have observed how it's done at BASF is that all the metal, let's say, and all the linkers end up in your product. So there's a zero discharge of the starting materials. Okay, so basically you're mixing the metal ions and the organics together, and then you get a precipitate, a solid, that has all the things that you've added in. Okay, so that's a zero discharge synthesis. The other thing is that at the end of the journey of this material, all you have to do is add acid to it, and that separates the metal from the organic. And then you can reassemble the material, again, using zero discharge process in water. So yeah, we have thought of that, because we've been developing also the natural gas tank. Natural gas is cleaner than petroleum. So we've been developing with BASF the natural gas tank.
Thank you.
But when the oil prices went down, that became not viable economically. So the automobile companies were not interested because oil was just too cheap. So I sometimes tell my students that we as scientists have to solve intellectual problems, because ultimately when you go all the way to society, whether your invention is adopted or not has nothing to do with science. It has to do with society's will to change. And I hate to say it, but humans have a habit of never doing anything about a problem until it is at their doorsteps, eating away their family or something like that. So we have to be harmed personally by the problem before we do anything about it as a larger society. So I like to emphasize that I think the problem is technologically, I think we can make progress towards a solution, but the social and political issues, like Banks said, are much, much tougher to solve.
Thank you, Omar. So, Melanie, and I'm sorry, after this question, we're going to have one more question after that, and then we're going to go to lunch where I encourage you to continue the dialogue, okay?
Well, thank you. Well, thank you all for great presentations. My question is for David. I find it fascinating that you can help people who are already infected with FENT. Can you tell us more about how we deal with our own air droplets?
Yeah, absolutely. So so understanding that the natural function of airway clearance is to capture much of what we inhale that actually passes through the larynx. In the upper airways, on this mucus layer, the ability to reduce the aerosolization of that material, the re-aerosolization of that material on inhalation, lowers the probability of whatever you inhaled getting deeper in your lungs, whether it's carbon, soot, or allergens, carcinogens, pathogens. And so, and I would argue, and I think that Ad reached out to me about a year ago, and we began this conversation. I would argue that part of why masks, I think, are a really good idea, both as a prophylactic and also once you've been infected, is that you're reducing, so you're just making the upper airway clearance work better. Now, in terms of the evidence for reducing movement from the upper airways to the lower airways, or the fact that respiratory droplets are actually carrying a pathogen lower in the lungs, I have always been fascinated by experiments like those that Chad has done, where and he talked about yesterday, where he's instilling virus in the nose or in the trachea, and then very quickly the virus is everywhere in the body, and when the clearance is actually moving the other way. So I think that's there's a lot more work needs to be done, obviously, and we last night began a conversation with John around kind of large-scale studies that need to be done looking at prophylactic and therapeutic effects.
Thank you. So last question, please, Dan.
Thank you. It's been fascinating to hear all of you. Omar, I share your optimism about technology. I would remind you, though, that the Apollo program that sometimes people talk about as inspiration was a single country and a relatively minor acceleration of a program that actually existed in the Eisenhower administration. It was a 20-year program, and Kennedy accelerated it to 10 years. Still an extraordinary thing, but I think a better analogy might be saying that we're going to do a Manhattan Project, except instead of starting in 1942, we're going to start it when Becquerel discovers radioactivity in 1895 and 1896, and then it's a much more difficult challenge. I think that's more along the lines of what we actually face in terms of innovation. I think this collective action problem is really at the heart of what we're talking about, and David, you brought that up. It's unbelievably hard, and when I think about COVID, and a lot of this discussion at this last 2 days have been about COVID, I've been to many workshops online about COVID and climate change. I think there are a couple of lessons, and we were talking about this at dinner last night. Number one, that I think when it comes to the collective action part, we've failed terribly, David, and I think you would agree with this. Just look at the vaccines and how unequal their distribution has been. We're getting a third vaccine in the US, while many countries don't have any access to vaccines. That does not bode well for our solving a truly global collective action problem. On the other hand, I think there is some optimism about how quickly we changed our behavior, how much the world, not perfectly, but how much the world did change in response to this pandemic. And I do see seeds of hope there, and I'd love to hear your thoughts, David, others, about that. Of course, real technology, Omar, as you know, requires trillions of dollars of infrastructure, and that's not something we're so good at either. But we have to get started, and I think in the simple idea of an aerosol spray that protects people from air pollution, I think those are the seeds of hope for the world. So I'd love to hear your thoughts.
Thank you, Dan. Yeah, several months ago, we wrote a commentary that many of you signed related to all that's being discovered right now, and so much has been talked about at this conference, and related to the air we breathe, and listening to Omar, the water we drink. And as Dan has talked about, the solutions are both meeting great challenges and maybe decades or longer in the future. But there are things that we can do right now, and it's sort of unconscionable, which again has been said by many people here, that there are kids who are being born today, 1.6 billion kids who are in K-12 range, 1 billion of whom are in multidimensional poverty. Many more than were just a couple years ago because of the pandemic, and they're pretty much breathing dirty air, they're pretty much needing food, and so they can't go to school, among other things. And the idea that we would not be doing something to help them right now is really crazy. And so, yeah, I think we have talked about, Lori, you've talked about, and we were speaking last night with Goran and Peter about another commentary that we all write, which I think I'd love to help write with all of you. And I think there's many things that have been discussed here about things that can be done. And one of those things is, I think, airway hygiene, and I think that data has to be collected. We had a conversation last night with John about what the WHO would need to see to make an opinion on the value. A lot of people have talked, including Akiko Iwasaki, about the importance of humidity and getting that solution in a way to respiratory health and WHO attention. And so here's an intervention. What would be required really for the WHO to opine? And you were really helpful in the conversation last night, John, that there's some major studies that have to be done in different regions of the world. And we'd like to do that. And who's we? I think this is a charitable effort. And so whether it's a charity that you lead or it's a charity, but I think it's a charitable effort that needs to come together here. I think that with regard to what we've been doing, we would really love to contribute to the building of systems that are super simple and super rugged, that work in an environment like what Carol has described. This is salt and water, the ability to allow anyone to make these things in those environments is there, and again, the bottom line is, can we keep everyone, but particularly young people, can we keep their airways hydrated? Even though they may be breathing dirty air or dry air. That seems like a really achievable goal. It's about 20 milligrams of water a day. And yeah, so anyway, that's something we're talking about, and I'd love to really get all of your thoughts on a really tight commentary that addresses everybody's thoughts, but very action-oriented.
We'll make sure that we keep this dialogue going, but I think we should also hear from Omar, since you addressed the technological challenges, and I'm sure you have.
I would say that, I pointed out to the Apollo program or the Manhattan Project because they were a united effort. There hasn't been something like that on the international scale. It would be nice to solve these problems. But we have even a bigger problem than that, that each one of us can do something about. And that is the problem of educating the what I call the emerging scholars, the young people in the world. 90% of those less than 30 years of age live in the developing world. And each one of us can do something about that in the sense that we're all experts in different fields. We can always seek out regions of the world where we can work and collaborate with the local talent and talk to them, mentor them, exchange ideas with them, but engage them, maybe a day a year, 2 days a year. We've been doing that with a program that I've created at Berkeley, and it's quite transformative because education is really at the heart of change. And if we can't bring those less than 30 years old, those young emerging scholars along, what kind of future are we looking for? Okay, what kind of future will we have? That especially in the developing world, they're neglected right now. But we as professors, as experts and so on, we can volunteer a day or two or a week out of our schedule. And many of you, or many of my colleagues have volunteered in this way. We all want to do it. We need to actually get it done. So I would say that could move things in the right direction to bring those people along so that they have a brighter future and our planet can have a better chance of surviving all these problems.
Thank you, Omar. And we're going to let Omar maybe get some sleep tonight or go on to his next activity. But I want to thank you all again. We all agree that we want to continue this dialogue, continue doing what we do well, and figure out ways to collaborate so that we do move towards a better future for ourselves and those that come behind us for many generations to come. So thank you again. I invite you all to lunch. Unfortunately, I can't invite you, Omar, but I appreciate your being here. Thank you.
It's nice seeing you all. Yeah,
Thank you.
take care.
Thank you all.